Hi guys, so I got a microphone from Mr. Raymond. Hopefully the quality is 300 times better. Hopefully the test went well and you enjoyed your day off. Here we go in chapter 10. Chapter 10 is about searching for the truth. So remember we said it's really unrealistic that I really truly know the true proportion of every person that watched Survivor. Or it's really hard to believe that I can actually ask every single household how much they make. So this chapter is about doing a sample, and we are searching for the truth. At what point can we go out and publish our findings, go to the newspapers, call up the TV stations and say, we know for sure we just figured this out, and how confident are we? So this is what this is about. How long can you expect a AA battery to last? What proportion of college undergraduate students have engaged in binge drinking? Is caffeine dependence real? These are the kind of questions that we're going to be able to answer. Now, is it possible to test every single battery or survey every single person? No. We know that that's really unlikely, too expensive, it's not going to happen. So can the true parameter, now remember parameter is population, so can the truth of the population ever really be determined? Not often, not exactly, but we have enough ability to get close. So at what point, when and how can we draw conclusions about the population? So when can we publish our findings, and how sure can we be? That's what we're trying to figure out. That's called statistical inference, and we've brought that word up a few times earlier in the chapter, or earlier in the year. This is basically what the whole end of the book is going to be about. This is going to be publishing our findings, calling up the newspapers. How confident are we? How sure are we that we want to tell people to go use this new cancer drug because it's really going to save your life? That's what this is all about. Can we be certain that our conclusions are correct within a certain confidence? That's the title of this. We're gonna have a certain amount of confidence. And what about sampling variation? We know every time we go out and do a new sample, we're going to get a different answer. So how sure can we be? So that's what this is. Confidence intervals allow us to determine how comfortable we should be. Now, confidence intervals are based on long run behavior. That basically is the definition of probability. So we're going to take what we know about how things behave over many trials, which is probability, and we're going to look at our findings, and then we're going to determine how confident we really are. None of this can be done if we don't use all the stuff that we've learned so far this year. So that assumes that we did a proper study. It assumes we have a random sample. It assumes that we're practicing replication, randomization, control. We're doing all that good stuff. Otherwise, it's pointless. Garbage in equals garbage out. If you do a crappy study, of course you have crappy answers. So we have to assume that all of this is happening. Okay, so there's your intro. So here we go into into section 10.1.1. So you can pause this for a second and read it. But basically, the school wants to start advertising what the IQ score is of all their students that come in. Problem is they have 5,000 freshmen, and they only asked 50 of them. They did get an X bar because it came from those 50 students of 112. So is the mean IQ score, is the true mean, is the mu of all the big city freshmen exactly 112? Well, no, we know it's not. We know that every time I asked a different 50 students, I would get a slightly different answer. So we know that there is sampling variation there. What does the law of large numbers tell us? Well, the law of large numbers, you know this, that the more and more people we ask, the closer we're going to get to the truth. So we know 50 is a decent number. We know 112 is got to be close to the mean, because the more and more people we ask, the closer and closer it gets. Now, how close exactly is it going to be? We're not sure, but we know a few things that can help us figure it out. And how would the sample mean vary? So basically, what am I really trying to ask you here? I'm asking you how spread out it's going to be. So how is the mean going to vary if we took many, many, many samples of 50 freshmen? Basically, I'm asking you the standard deviation, right? Now, we already know some stuff about this. We just got done learning a whole bunch of stuff about this. So let's remember what we know from chapter 9. We know that the sampling distribution of X bar describes how X bar will vary in many, many, many samples. More specifically, what is the sampling distribution? The sampling distribution is every possible combination. Every possible combination of 50 students. Well, in this case, 50, but whatever your n is. So in this case, sampling distribution tells us what's going to happen. And what is it that's going to happen? We know that if we do every single possible combination of 50 students, then the repeated mean of all of those students is eventually going to fall at mu. We know that. Okay, we also know the standard deviation. This is just your formula that you used from the last chapter. We've got sigma over the square root of n. That's your formula you just did on the test. If we do every possible combination of 50 students, my standard deviation is going to be this. Now again, if it's unrealistic for me to really know the mean, they tell us here, suppose we know the standard deviation is 15. Is that realistic? It's really not. But again, that's a luxury we're going to give you and then we're going to take away from you. So somehow we know that when we ask over and over and over and over, standard deviation is going to be 15. So that means that in a group of 50, my standard deviation is going to be 15 over the square root of 50, which is 2.12. And save that because we're going to use it on the next page. We also know that the central limit theorem tells us that because n is large, remember we're going for about 30, but proceed with caution if it's anything under that. The distribution is going to be close to normal, so that's good. Because if it's close to normal, then what can we use? We can use z-scores and all sorts of other stuff. Okay, so that's what we already know. And here's what we're going to do with it. Now, I did a video a couple minutes ago and I babbled about this for 10 minutes and I would have thoroughly confused you. So I started over. So here's where I want you to go. And we're going to go to the end and we're going to look at this picture first and then we'll come back. So here's the idea. The idea is that we're searching for the truth. So we know some X bar. I want to know the truth. So I can do many, many samples of 50, which would be my X bars, and I'm searching for the truth. That's what this whole chapter is going to be about. So the big idea is this. I assume you all are sitting in your normal seats. So let's say I know that Bailey right now is sitting within 15 feet of Logan. Right? So if I know that Bailey is within 15 feet of Logan, then I also know that Logan is within 15 feet of Bailey, right? So I can reverse my logic. So basically, here's what we've learned this far in the year this far. We know that if I have a distribution, and if I know that the true mean is right here, this is mu, then the 68, 95, 99.7 rule tells me that every time I go out and get a piece of data, that 95% of the time it's going to be within 2 standard deviations of the mean, right? So 95% of the time it's going to be within here. So here's the idea. If every time I go out and I get an X bar, if X bar is going to be within 2 standard deviations of the mean, in other words, if Bailey is going to be within 15 feet of Logan, then if I find Bailey, then Logan should be within 15 feet of her. So if X bar is going to be within 2 standard deviations of the mean, then if I can find X bar, mu should be within 2 standard deviations of that. I'm just reversing my logic. So I have this distribution. Mu is sitting right here. Here's my 2 standard deviations away, which I could drag straight down this picture. So if I go straight down here, except my pen is very crooked. Then here's a whole bunch of samples. I went out, I found this X bar, I went 2 standard deviations away and 2 standard deviations away, and I caught the true mean. I went out and I did this sample, I went 2 standard deviations away, 2 standard deviations away, and I caught the true mean. I did this one here, 2 standard deviations, I caught the true mean. This one here, a little bit further out, but I still caught the mean. Okay, now this one here, so 95% of the time, I do an X bar, I catch the mean. I do an X bar, I catch the mean. I do an X bar, I catch the mean. 5% of the time I don't. So this one right here was one of my unlucky ones. I found an X bar, I went 2 standard deviations away, and I didn't catch the mean. But the idea is this, 95% of the time we will. So we can say with 95% confidence, this is where confidence intervals come in, with 95% confidence, that we will catch the true mean if I find X bar. If we did a proper study and everything's good, 95% of the time I will catch the true mean. That's the idea. So I'm going to let you can read through all of that and look at the pictures on your own. But I think it's just a bunch of babbles. I think it's easier the way we just talked about it. So here's what we do need to know. If my X bar equaled 112, and my standard deviation from the last page was 2.1. So 95% of the time, I expect the true mean to be within 2 standard deviations of that. So if the standard deviation was 2.1, if I times that by 2, then 95% of the time, I expect it to be within plus 4.2 and minus 4.2 of 112. So those two numbers, if I subtract 4.2 to one end, add it to the other, then 95% of the time I expect the true mean to be between there. So here's what I can say. I can say I am 95% confident that the true mean is somewhere between 107.8 and 116.2. Okay? You can read that. Statistical inferences, it uses what we know about many samples to express our confidence in one. I know if I do it over and over and over again, 95% of the time it's going to work. So I can be 95% confident in one sample. So this is just saying what I already said. We are 95% confident that the true mean is somewhere in this interval. So here's how your confidence intervals are going to look. You're going to have some level of confidence. You can set what that level is. Now, in this example, we did 95%. We'll stick with the 95, 68, 95, 99.7 rule for your homework today. We'll change that tomorrow. It's always going to start with your X bar. So you're going to have some X estimate, which will be the X bar that you calculated, and then some margin of error. So in this case, it was plus or minus 2 standard deviations. So it's going to be some distance away. So X bar, hold on, plus or minus some degree of standard deviation. Either 2 standard deviations away, 1 standard deviation away, something like that. The confidence level, which gives a probability. So your confidence level is your 95% confidence. So the idea is that the interval between 107.8 and 116 captures the true mean, we think 95% of the time, or it doesn't 5% of the time. Now, we have no idea to know whether we're in this group or whether this group. We're never going to know. But we can say that we're 95% confident that we should be. So either you're one of the 95% lucky ones or you're one of the really unlucky 5%. But we don't know. We know we're 95% confident that the true mean should be in that range because we did a good study and we did everything we know how to do.